So, welcome to this last lecture of this lecture series. Uh, I would not say lecture, but problem solving session. Um, so, some announcements is I'll upload the week 6 video in this week only, so you'll be able to look back, so and refer to. And also, if you think that you need to give any suggestions that how in future this uh, problem solving sessions should be conducted, so you all can give your feedbacks, which you as you know that there's already been a feedback page been opened up, so you all can give your feedback on those sort of things, so that it will be helpful for me also in future if I take those sort of classes. And I have posted my email ID in this the chat box itself. So as your exams are nearing, so if you face any kind of problem, just ring me up there. Okay, so I'll be happy to help you all. And during classes, if you find any problem anywhere, just interrupt, and I'll be in my flow, but just please interrupt when you find that you are not able to understand at some point. Okay, so that's those things. Okay, okay, fine. Okay, all right. So let me just share my screen. Okay, so you all can see my screen, right? And hear me properly. Okay, okay, fine then. So let's move on to the questions. And yeah, so these are the questions. So the first question is the first three peaks in the XRD pattern of a FCC structured material. So basically, what you have to think about is that they are the Miller indices. The Miller indices HKL. All right, for FCC HKL should not be mixed, right? As you know, should not be mixed. Okay, meaning that both pairs, like in pairs, they should not be they should be both even or odd. Okay, so why this is so? So I'll tell you. Okay, so I'll just do it in the for FCC. You know, there are four atoms, right? So there are four, so there are four letters. So one is at CO00. Okay, another is at half half zero. Another is at half zero half. Another is at zero half half. Right? So basically these are the centers. Okay. So when you calculate the structure factor F X K L, that would be F times E is to 2 pi I H into 0 plus K into 0 plus L into 0. Alright, plus E raised to 2 pi I H into half plus K into half plus L into 0. So likewise, plus E raised to 2 pi I, the next is H2 plus K into 0 plus, okay, to 2 h into 0 plus x. Okay. So in this case, so what we have is f1 plus e raised to h plus k plus e raised to h plus l plus e raised to pi I k plus m, right? So now for this to be finite, for this h l to be finite, is individually has to be finite, right? So if h plus k is even, the e raised to pi I term survives. H plus l is even, e raised to pi I term survives. And k plus l is even, e raised to pi I term survives. So the exponent here, exponential term has to survive. It has to be 1. It has no option other than being 1 and minus 1, right? Because h and k are all integers, so it can be either odd or even, right? So for this, if hkl for f hkl to be finite, to be non-zero, h plus k, h plus l, k plus l, they have to be in pairs. They have to be odd or even in pairs, right? Okay. So they should not be mixed. They should not be mixed. Okay. So in that case, what you have is HKL should, because if you combine all this, H and K individually has to be even or odd, H plus L individually has to be even or odd, and K plus L individually has to be even or odd in pairs. So HKL should be even or odd. Okay. So now going back to the original problem, you're given 4 options, right? But look at the last option. So 1 1 1, right? So individually they are h, k and l. Individually h and k are order even. So if you add them up, they'll be even. Okay. And 200 and 220 suffices the condition that they individually are pure odd or even, they're not mixed, right? So the last option would be the correct answer, because you see for 100 it is not the case, 111 also is not the case, because it can be correct, it even is correct, and but 200 it is also correct, but 100 would not be correct, because in that case they individually would be odd. So 121 also does not suffice, 220 will suffice, 200 will suffice, but 311 would also suffice, but in this case 311 would also not suffice, right? So 220 will also suffice, but in combination they have to satisfy all the three. So the first three peaks, let's say, so for 111, 200 and 220, they are the first three peaks, in fact. Okay, so the third option is 200, it is suffices. 311, my bad, it has to suffice, all right? So 220, but they are not the first three peaks, all right? So 111 is there for the FCC XRD pattern, 200 is the following, and 220 is the next, all right? So although option B, they suffice the condition that H, K, L, and they should not be mixed, but they are they're not the first three peaks of the FCC XRD pattern. So option 4 would be correct. Okay, so option 4 would be correct. Okay, so let me ask if you understand properly this first question. Why is it so? If do you have any problem, guys? Understand? Please ask if you have any problem, because only knowing the answer would not help you a great deal. Okay. Is there any problem? Okay, fine then. Please try to understand each and every point. Okay. These assignments, they will be done. But when you are in exam, you have to look back to this sort of classes only. Okay, where you understand the basics, how it's done. So basically what happens in lectures, that professors teach the basic materials, but you have to understand by doing problems, by solving problems and asking questions. All right. So yeah, if you don't have any problem, so let's move on to the next question. So following is or are not correct about X-ray diffraction, statements about X-ray diffraction from crystals. So intensity of the peaks is proportional to the half of the square of the structure factor, which is not correct because it is proportional to the modulus of the square of modulus of the structure factor. So it's not correct, so you have to take it. Structure factor is dependent on the shape and size of the unit cell. So it is not dependent on the shape and size of the unit cell, but rather it is dependent on the position of the atoms in the unit cell. That is the third option. Okay, structure factor is also independent of the elements of in the crystal. So basically, it doesn't depend on what elements is sitting. So let's say for NaCl, so basically it will depend on the position of the atoms in the unit cell. So it doesn't matter where sodium ions is sitting or chlorine ion is sitting, it doesn't matter. Okay, but for NaCl, so sodium sits at all the corners, and chlorine sits at all the corners. This is a simple cubic structure and face centered cubic FCC, and sodium sits at the interstitials. All right. So basically the structure factor in that case would be dependent on the position of the atoms in the unit cell. So the second option is also incorrect, that's why you have to take it. So structure factor depends on the position of atoms in the unit cell, that is correct. And also structure factor is independent of the elements in the crystal, it is also correct. Rather it depends on the position of the elements in the crystal. Okay. So now what you have here is a problem, a similar problem that has been taught in the lecture, but let us just do it anyway. So this is 2 theta, this is theta, this is sine squared theta, this is h squared plus k squared plus h squared, and this is sine squared theta over h squared plus k squared plus h squared. So 2 theta is given. The 2 theta is given. What you have is 38.0, 44.2, 64.4, 77.2, and 81.4. So your theta values would be 19, 22.1, 32.2, 38.6, and 40.7. And these are in degrees. These are in degrees. So this is 0.1 sine squared of this angle theta. So 0.11, 0.14, 0.28, 0.38, 0.42. Okay. So basically, let's start with FCC, a simple cubic, right? So simple cubic, you have to deal with 1, 2, 3, 4, 5. All right. Okay. So what happens is that if you divide 0.11 by 1, 0.14 by 2, so basically what you have is lambda by a whole squared. So you have is your so let me just check if I have done correctly. Yeah. So 2b sine theta is equals m lambda. From that formula you have lambda by 2a whole square times a squared plus squared plus l squared is equal to sine squared theta. So if you take this in this, so sine theta over h squared plus k squared plus l squared, in that case lambda by 2a whole square will be in that left side, and so Sine square theta by h squared plus k squared plus l squared will be a constant term for every sort of planes, right? So basically what happens is that your for all this sort of scenarios you will have this ratio as constant, but it doesn't happen for simple cubic, body centered cubic and diamond cubic, as you will see, because body centered cubic as you divide by these numbers, it will not fetch you the correct constant ratio. But what happens for FCC, you'll see what happens for FCC, you see, not all these values are allowed, right? As you can understand, because FCC, what you have to keep in track is that h plus k plus l is either pairwise, odd or even, or so that case, okay. So pairwise, both are even or both are odd. So by that token, for FCC, let's say for FCC, we have this is 3, this is 4, this is 8, this is 11, this is 12. So 3 is 1 squared plus 1 squared plus 1 squared. 4 is from 2 squared plus 0 squared plus 0 squared. So basically this is 1 squared plus 1 squared plus 1 squared. Okay. 2 squared plus 0 squared plus 0 squared. 2 squared plus 2 squared plus 0 squared. Okay. And this is your 2 zeros and so this is 3 squared plus 1 squared plus 1 squared. So by that practice, you can always verify your first question answer, right? So 111, then is 2200, and then is 220, and then would be your 311. Okay, so 311 would be your the next set of planes. And the 9, this is 10 11, and what you have is 4. You can't have 2 2 4 9. You have 2 squared plus 2 squared plus 2 squared. Okay, so this is your next set of planes. So if you divide each and every one by 0.11 by 3, both will have this you see 0. You can do it yourself. 0.11 divided by 3, that it will fetch you 0.036 sort of something. 0.14 divided by 4, it will also, so basically all will fetch you this 0.035. okay, so that's because for FCC type of structure, so this is the process you follow in determining what sort of crystal structure is there and what's the lattice parameter. So basically what you do is check for this sine square theta over h squared plus k squared plus l squared ratio. All right, so for FCC only you find that this ratio is constant, but for other cases it is not constant. Okay, yeah, so y'all can hear me, right? So you're able to follow these questions, right? So my screen is also visible and you're able to understand what's going on, right? So so it is on your part that you ask questions. Okay, so in the middle I'll be stopping and asking that if you have any questions. So if you have any problems in understanding what I'm teaching and what not, so please interrupt and ask, or else you can write in the chat box. I'll check meanwhile in between. Okay. Okay. So basically the correct answer would be for FCC, you have this condition satisfied. Okay. So the next question is which of the following characteristics of materials can be accurately determined by using X-ray diffraction technique? So one is that vacancy concentration in the material you can't do with XRD. So that can be done. So identification of phases in the material, that can be done because if you have a stoichiometric combination of different types of materials, like different types of elements, I would say, forming a compound with different stoichiometries of the respective elements, you'll be able to understand the phases, because at those certain elements, it will have definite peaks, right? So it will give you the definite peaks if you do a XRD measurement. And determination of strain in the crystal, that is also quantified, as you also know from the video itself. All right. So determination of strain in the crystal is another. Atomic size measurement, that you can't do, because basically you can determine the atomic distance, like unit cell distance, what is the lattice parameter, okay, but you can't determine the atomic size. Okay? So identification of phases in the material and determination of strain in the crystal would be your answer. Okay, so yeah. So which of the following is a diffraction condition for diffraction from a BCC lattice? Okay, so as you know that for BCC you have atoms at 0, 0, 0 and half, 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 like at the body center. So your structure factor would be h times 0 plus k times 0 plus a times 0 plus e raised to 2 pi I times half h plus k plus l. Okay, so what you have is f1 plus e raised to okay, so pi I h plus k plus l. Okay, so basically what you have to do is, for this to survive, for this not equal to 0, so h plus k plus l must be even, because even times pi I will give you 1. Okay, must be must be even. So your correct answer would be h plus k plus l must be even. Okay, so this is quite simple. In a powder diffraction experiment using cobalt K alpha radiation of wavelength 0.179 nanometer, what is the diffraction angle for the first order 220 set of planes from the BCC structured iron, 220 set of planes from the BCC structured iron with lattice parameter 0.2866. Okay, so for just structure for BCC. Okay, so for BCC, for 110, as I told you in the last lecture, so this I flash to you about the last lecture, or maybe I'll just move into the 7 assignment if I may. Okay, okay. So for BCC, you see that there's a crystal, it has to span the entire A and B axis, right? Not the C axis. So in that case, your BCC 100, sorry, D would be A by 1 square plus 1 square plus 0 square, that is A by root 2. Okay, fine. So in that case, what you have here is also talked about 220, which is a basic multiple of 110 plane, right? So there's a set of family of planes. So basically what you have is you have to use the Bragg's law, that is 2b sin theta is n lambda. Okay, and for BCC 110 d is a by root 2. Okay, but for 220, what you should have is a by let's check. Yeah, so a by 2 square plus So d is, so basically you have 2 into a by, so, so basically what you have is okay, so okay, fine then. um 2 square plus 2 square plus 0 sin theta times, you have said that it is first order, right? First order angle of first set of things. Okay? So that is 1 and it is lambda. So basically you put 2 times 0.179, sorry, not 0.179. So uh, let's parameter is 0.286 over root 8 and sin theta is equals lambda is 0.179. So basically let's just calculate. So you also calculate along with me. 0.2866 times root 8 divided by 2. Okay, so so sin theta, is equals 0.88. Theta equals sin inverse 0.88. So this is the sin inverse of this. It's 62.03. Okay, times 2. Oh, that would be around 124. Okay, so theta comes out to be 62. Okay, now you have asked about the diffraction angle. So diffraction angle is basically 2 theta. So it is 124. So the first question, the first option will be right. Okay, so basically what you use is the Bragg's law, and 2 to 0 sort of planes, you calculate the interplanar distance, and it should not be a by 2, because for going to 2 to 0 planar distances you have to traverse all the a and b axis, right? So in that case it is only a by h square plus k square plus l square. Okay, root under. So that is done. Which of the following is there are zero dimensional defects? Okay, so that would be your Schottky defects, which are basically anions and cation vacancies. Okay, Schottky defects and interstitial atoms. Okay, so interstitial means if this is the set of arrangement of atoms, so this is an ordered set of arrangement. Okay, now what you have is, your interstitials would be like this. Sorry, this. So correct. So this is the your interstitial. This is your interstitial atom. Okay. So these are zero-dimensional defects. So which of the following things are referred to as equilibrium thermodynamic defects? Okay. So basically this defect is sort of defects that depend on temperature, and as you know that vacancies, or how many sort of it's not dislocations, so vacancies you can have depending on temperature, how many vacancies you can have. So on equilibrium scenario, the thermodynamic defects, they are the vacancies. All right, and you have already watched in the videos that how some defects can be there depending on temperature, and we explicitly worked out this free energy calculation. So that what can be, let me just give you the scenario, that last formula, last master formula, and that would be your yes. So, yeah, so n, small n, number of defects is exponential minus delta f by kd. So N is number of sites, and GF is the enthalpy of having these defects, and KB is a Boltzmann constant, and T is a temperature. So depending on temperature, these vacancies or these defects will be increased or decreased. Okay. So that is vacancies are equilibrium thermodynamic defects. Okay. So Schottky defect, as I already told you, is pair of anion and cation vacancies. Okay. It's recording. Yeah. Third question. Okay. Okay. Third question is okay. So see, for as you know, for let me just for simple cubic, all HKL are allowed. Is that right? Let me ask you. Is that what you know? Is it simple? Hello. So for simple cubic, you know that all HKL are allowed, right? So have you watched the video? Okay. So let me just please watch the video carefully. Okay. So it's all there in the video, but anyway, right. So for simple cubic, for for simple cubic, there's only atoms at 0, 0, 0, right? Okay. So F is to I 8 times 0 plus 8 times 0 plus 8 times 0. So it doesn't matter what HK and L you are having, it always results in okay, possible. Alright. For BCC, as I've already told you, for BCC is H and K plus L must be even, and for FCC, both in pairs they have to be even. So if you don't write down the things, so 1 0 0, okay, so 1 0 0 10 for BCC, so for simple cubic BCC FCC, okay, this is allowed. For BCC, all the terms have to be even. H plus K plus L has to be even, right? So this is not allowed. And for FCC also, pair has to be even, or pairwise have to be even or odd. Now 1 1 0 it's always allowed in simple cubic. Let's say for BCC, it's allowed. Okay. So and for FCC, it's not allowed, right? But for 1 1 1, it's allowed in simple cubic. It's allowed in BCC because they're not all do not add up to an even integer, and this is allowed in FCC because pairwise is odd. Right? So what happened there, Simran, is that yeah, in this case, not all HK and L are allowed for simple cubic. For BCC, for all are allowed for simple cubic, but if you divide it by sine squared theta over h squared plus k squared plus l squared, all will not result in a constant ratio, right? You have this has to be constant, right? So basically you do have the formula that 2d sine theta is equals n lambda, right? Let's just put n equals 1. Okay. So lambda over 2 sorry, lambda over 2d is equals sine theta, right? Okay. Now d is e by a squared plus k squared plus l squared. Okay. All right. So lambda by 2a times a squared plus k squared plus l squared is sine theta. Okay. So just sine square theta over h square plus h square plus square. This is correct. So basically, lambda stage, you are doing the experiment with a fixed wavelength, and the material you are using, it has a fixed lattice parameter. Okay. So if the left hand side is constant, this ratio should also be constant. Is that you are getting my point, right, Simran? Hello. Huh. So is all the points are well explained, right? You do get my point, right? So what's the thing? So basically now what you have to look out for is that which planes are allowed for simple cubic. Okay. So if I just okay. So basically all the H scale are allowed. So 1 0 0, 1 1 0, 1 1 1, and then 2 0 0, 2 1 0, 2 1 1. These all are allowed for simple cubic, but not allowed for FCC and BCC. Okay. So I took out this FCC example, and you just have to write down these planes. You just have to write down this plan. So after 110, what will come? 200, then 210, then 211. Okay. All right. Then 300, that will come. Okay. So in this way, you keep on writing these numbers, and you do this h squared plus k squared plus h squared. Okay. But not all of these will be allowed for CC and FCC. Okay. And you have to keep in mind that this sin square theta over h squared plus k squared plus l squared will have to result in a constant ratio, because the left hand side is already constant. So for FCC case only, this thing suffices. This thing is maintained. Like if you divide all the sine square theta, so basically what you are given is 2 theta. You do a theta by dividing it by 2, and you calculate sine square theta. Now you have to check out for this ratio for h squared plus k squared plus l squared. For simple cubic, it would be 1 2 3 4 5. Okay, because all the planes are allowed. Are you getting my point, Simple? If not, I'll explain again. You're getting my point, right? So for simple cube, what you have to do, sorry, you have the planes that are allowed will be 1 2 3 4 and 5, because 100 is 1, 110 is 2, 111 is 3, 200 is again 4, 211 is 5, because you have to do h squared plus k squared plus l squared. In that case, for simple cubic, if you divide sine square theta over by these numbers, you will not have the same ratio. Please just go back and look at it yourself only, okay? Because I'll not do this simple cubic and body centered cubic. You have to check. This is a sort of a homework, and if you find a problem, just write back to me, okay? Because something has to be done on your own. So this is a good practice. You do this at this time only, okay? So for simple cubic, all the planes are allowed, but the ratio will not be the same. For body centered cubic, not all the planes are allowed. In that case also, you'll see that sine square theta over this h squared plus k squared plus l squared will not give you the same ratio, same constant value. But for FCC, you divide all these numbers, the planes that are allowed. So 111 plane is allowed, 200 plane is allowed, 220 plane is allowed, 311 plane is allowed, and 222 plane is allowed, right? So by this formula, what you have is divide this by this, divide this by this, divide this by this. You have the same constant value of 0.035. So for this case only, you have to understand this, as this criteria is satisfied, this ratio is constant for all the cases, for all the two theta angles. In that case only, you have this FCC type of structure. Okay, so that is your answer. So are there any further problems? Simran, am I clear to you? Okay then. So if you face any kind of problem, just do it yourself, and if you face any kind of problem, just okay. So for now, do you understand it? Okay, so just check it out yourself by explicit writing for BCC and simple cubic. Okay, because BCC you have to keep in mind that H plus K plus L has to be even. So not all the combinations will be allowed. So for 100, BCC will not have this 100 diffraction plane, right? But for 110, it will have. Then again, for 111, it will not have. So first would be 2 H squared plus K squared, 110. Okay. Then you have 4. Then you have 6 in this case. Okay. So just try on those things. Okay. Yeah. Where? Okay, so I'll skip this 10th question for now. I'll come back to it later because it needs a bit of a explanation. So which of the following is or are true for an age dislocation? So there are two types of age dislocations. One is uh, you know there are one is the age dislocation and another is so for dislocations, line defects, there are age dislocation and the other is your screw dislocation. Okay, so along the plane, along the dislocation plane, the Burgess vector is perpendicular to it. Okay, so this is a theme that if there's a vacancy, it will try to create a strain on those vacant sites. So there will be dislocation of the lattice sites. So along these dislocation planes, the Burgess vector would be perpendicular to that. Okay. So basically, dislocation line is perpendicular to the Burgess vector. Okay. And motion of edge dislocation is parallel to the Burgess vector, which is of course the case because what you see is that it's parallel to the Burgess vector. Yeah. Motion of this motion of edge dislocation. Okay. So motion of edge dislocation. So along this Burgess vector, you have this motion, right? You have this motion where you have this Burgess vector and there's a extra plane you have to traverse. So if you move forward 3 steps in each of these directions and 4 steps in each of these directions, so basically what you have for a dislocated lattice site is that you'll cover one extra lattice point. Okay, because there's a dislocated lattice now. So the Burgess vector is along the motion of your dislocation. So the third option would be correct. Okay, motion of edge dislocation is parallel to the Burgess vector. So the 12th question, the Burgess vector of dislocations in case of BCC lattice is, this is quite informative. So you know from the video itself, this is a by 2 111 direction. So the length of the Burgess vector is a by 2 times 111 plane. Direction of 111 plane is distance of the 111 plane is that would be okay, yeah, that is 1 squared plus 1 squared plus 1 squared, that is a root 3 over 2. Okay. So that is length of the Burgess vector. So this is the Burgess vector for BCC lattice. Okay, if an element having FCC crystal structure has lattice parameter of 3.57 angstrom, what is the magnitude of Burgess vector? So for FCC, magnitude of Burgess vector is a by 2 times FCC crystal is, that is 1 0. So a by 2 times 1 squared plus 1 squared. Okay, that would be a by 2. So a is 3.57 angstrom. Okay. So a by root 2 would be 2. This is very simple. So this is 2.52 angstrom. Answer. The modulus of and lattice parameter of copper at 30 gigapascal and 3.65 angstrom respectively. What is the elastic strain energy per unit length of dislocation line in copper. Strain energy per unit length is your force. Okay, so that is energy per unit length is your, if you have drawn this, so it has dimensions of force. So that is why the answers are all given in Newton, which is unit of force. All right. So shear modulus, sorry, okay, let me just write it. Shear modulus is given 30 gigapascal. Is 30 into 10 raised to 9 pascal. Okay. What is hand? Lattice parameter is 3.65 angstrom. So strain energy per unit length, strain energy per unit length is given by half times this is shear modulus G and copper R. Okay. B is the Borges vector. So half G into Borges vector. B squared. Okay. So shear modulus is given, but you have to calculate this Borges vector. For copper, it is said for copper, the structure is FCC. So B would be A over root 2. Okay. So half times 30 into 10 raised to 9 times A over root 2. Okay. So A is 3.65 angstrom. So that would be half into 30 into 10 raised to 9 times 3.65 into 10 raised to minus 10, because all you have to do is calculate inside. Okay, and this square. So that's simply 2 into 3.65 into exponential minus 10 divided by root 2 squared. Okay, so the answer comes out to be 9.9 into 10 raised to minus 10 Newton. Okay, so the answer is the answer is 9.9 10 raised to minus 10 Newton. Okay, yeah, that is the thing. The last question, although one question is left, the structure factor for ordered CSCl will be. So basically, what happens is that CSCl is a you know, simple cubic, and the chlorine atoms so basically sits at the face centers. Okay, this sits at the face centers. So 001 for chlorine, so 0 for cesium, it is 000, and chlorine it is half half half. Okay. So what you have is FHKl is F cesium exponential 2 pi I H into 0 plus K into 0 plus K into 0. Okay, plus F chlorine exponential 2 by I by 2, because H by K by 2 plus L by 2. Okay, H by 2, 2 by 2. So what you have here is FHK is cesium, okay, plus F chlorine e raised to I H plus K plus L. Okay. So now H plus K plus L is equal to I to 1. So in that case, FHKl would be FCS cesium plus F chlorine. But if H plus K plus L is odd, you have what you have is e raised to I pi is pi then minus 1. So you have HKl is FCA cesium minus F chlorine. So the third option would be correct. Okay. So what you see is that cesium atoms sit at body centers. Okay, body centers. Okay. So not at the face centers, but at the body center. Okay. That is the structure of cesium chloride, as you already learned in the, I might have said phase centers, but it sits at the, because it's half half half, it sits at the join now. Anyway, this will be recorded. So yeah. Okay, never mind. So tenth question I didn't discuss because I said that I'll go to it now only. But 11th question. So which of the following is or are true for an age dislocation? Okay. So age dislocation is that this is a perfect crystal, you see. Okay. So now if you just move 3 steps along this, 4 steps along this, 3 steps along this, and again 4 steps along this, you get back to the same point because it's a perfect crystal, ordered crystal. Okay. But now you have some lattice side atoms from the lattice side missing. Okay. So then only you'll feel some strain coming from this side, like this was the this if you have atoms from this place is missing, you'll have strains, you have stresses and strains from both these sides, and there will be a distortion in the lattice side. Okay. So if you go 3 in this direction, 4 in this direction, 3 in this direction, and 4 in this direction, you see that you are traversing a lattice side more. Okay. So basically, so this you understand, right? So basically, so this is the so this is coming out of the plane. I mean, uh, uh, these points are missing. These atoms are missing from these points. So basically, the plane of the dislocations would be out of the paper or out of the screen, right? Now, what you are traversing, extra traversing, the extra point that you are traversing is will be by then perpendicular to this dislocation plane. Is that correct? You're understanding, right? Like if you have this sort of a, let me just go to my screen. So if you have this sort of a lattice plane, and the dislocation plane will be along this side, right? Okay. So now along this you have these lattice sides, and you are traversing a distance more along this. Okay. As I saw you, as I flashed you the diagram. So this is the dislocation plane, and you have to traverse along this too, because you have to traverse four steps along this, right? As done in a perfect crystal. So if you traverse 4 points along this, you will traverse a lattice point more, because now the lattice is distorted. It is forcing you to traverse a distance more if you have to maintain 4 steps, right? So in this, for this reason, this dislocation plane is perpendicular to the Burgess vector, which is the B vector. Okay, and D is the dislocation plane, also shown in this diagram, right? So uh, uh, so in that case, let us see. So 11, dislocation line is perpendicular to the Burgess vector. All right. Yeah. I'll discuss. Okay. So there are some problems with it. I'll tell you. Uh, Also, which of the following is or are true for an edge dislocation? So that is done, and motion of the edge dislocation is parallel to the Burgess vector. All right. Because you see, motion of the dislocation, this is the dislocation points, and if you have to compress it, it is getting strained, so it will be getting strained along the Burgess vector, right? Because the plane is perpendicular to the Burgess vector, and it is strained in along the Burgess vector direction. The only point of drawing this Burgess circuit was to get the strain direction, right? So the Burgess vector is along this direction of your strain direction. Okay. So the option that motion of edge dislocation is parallel to the Burgess vector. So that would be correct. Is that okay, Simran? You are getting right. I mean, just you don't have to say yes to everything. But if you are facing any problem, okay, fine. So the next question now I'm coming. This I find it that I was having difficulty in seeing this problem because of the fact, like, right, like intensity I diffraction is proportional to the modulus of the structure factor, squared of the modulus of the structure factor. Okay, so for BCC, so let me just write out the planes. Okay, so 1 0 0 1 1 0 1 1 1 2 0 0 2 1 0 2 1 1. Okay, so the combination has to be even. Okay, so the first peak, it would come from the 1 1 0, because H plus K plus L is even in that case. Okay, so structure factor would be F1 plus E is to I H by 2 plus A by 2 plus N into 0, because for BCC it's 0 0 0 and half half half, right? So half, okay. So that is it. So F1 plus you have e raised to pi I into 2. Okay, e raised to cos pi I would be 2. Okay, so now what I have a problem with this question is that, which is my bad, because I was not able to understand what I would have done. So my feeling is that the so basically the next plane that would be giving a response would be your 200 plane. Is this understandable? First tell me this, is this understandable to everybody? Because then the HKL plane would be H plus K plus L would be even, and BCC has to satisfy this. So the next set of diffraction pattern would come from the 200 plane. But then again, also the F would be 1 plus 2F. So basically, I do not know what would be the correct answer. I'll think over this. I'll get back to you over this. Frankly speaking, I do not know what the answer would be. So I have to figure this out, right? So pardon me with this. So yeah, that's it. So question 10, I am not able to figure out currently, but I'll get back to you if needed. Or you can write back to me and ask for it. Okay. So I'll need some time before I can affirmatively say that this is the correct answer. Okay. So any queries, any questions with this? Anybody? Simran, unfortunately, I don't know. Maybe sample papers. Okay. 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 As the course is basically finished, yeah. I can understand I can understand where from you're asking this. Yeah. Okay. Okay. Sample paper, so I don't know, but mostly it would be along these lines, as I would know. But I don't know actually, but I'm guessing that it would be along this how these questions are there done for these assignments. But I'll have to get right to the support team. Okay, so then only I can have an answer. So because nothing of this sort is communicated to me. They are not communicated to you, but also not communicated to me, right? So I do not have the right to say this, but I'll always ask for them. So okay, so Venkateshan, and for everybody who was asking that what is the correct answer, so it's given that it's half, the first option, but I cannot affirmatively say that I am able to teach you how it's coming half. Okay, so I'll get back to you on this. So the correct answer is half, if not done wrongly. But so the first option is correct. Let me just write it. Give you an answer, but anyway. this is right as given by the team. So I was not able to get into it. So that is. So yeah, any question? Okay. So please, if you feel like, keep the feedback on this in this. Okay. Question number 8. I have to explain that. Okay. Okay. So which of the following is or are referred to as equilibrium thermodynamic defects? So basically, what you have to understand is that uh, these dislocations, grain boundaries or twin boundaries, they are not uh, the numbers, the number of defects, okay, they are not dependent on temperature. So equilibrium thermodynamic defects mean when you are in thermodynamic equilibrium, the temperature, there's a constant temperature, it depends on the temperature itself. So these vacancies or these defects, I mean, let's say for interstitials, this sort of things, they depend on the temperature. Okay. So number of these vacancies, it is given by this formula, is dependent on temperature. So if you increase the temperature, the number of vacancies would be more, and if you lower the temperature, the number of vacancies will be less. So that is why we are saying that vacancies are referred to as equilibrium thermodynamic defects. So in equilibrium scenario, when there is a constant temperature maintained, so it will depend on the temperature itself. So that is why they are defined as equilibrium thermodynamic defects. All right. Yeah, if you have any further questions, please ask, and if not, I'll just, yeah. And I'll of course post the video, because I am also being sent a reminder about updating the link of that video on that Excel sheet that you get in the course portal. So I'll upload this video in this week only. Okay. So before the question, my email ID is there. Yeah, email ID is there. You can always write to me. Okay. Yeah. Okay then. If you have no further questions, yeah, let's just end this meeting. Okay. Okay, bye. Thank you, everyone. And prepare well for your exams. And if you face any problem, just write to me. Okay, my email ID is given there. Okay. Okay, thank you.